So let me discuss a little bit the motivation, the model that I will consider, some literature review, and then I jump into the new dynamic programming approach that these slides propose. Okay. So let me first, although everybody seems to know, I'm sure everybody knows about the motivation, decentralized control systems on network. We mean multiple decision agents or controls with different information structures or patterns. Information pattern is the data strategies used to implement their actions. Of course, these were introduced by Hans Witsenhausen in 1960s. There are two famous papers written by Hans. The first one is 68, is the so-called Gaussian counterexample. And the other is a 1971 paper that discusses estimation and control. And I found this one to be very generic with respect to the model. Okay, with respect to the applications, I think these days, these problems that Witsenhausen was talking about are timely in many different areas, from transportation to network control and communication systems. But these are also problems of interest in economics and finance. So let me jump to the model so that we all have the same common frame of reference. I would discuss this problem as it connects to partially observed Markov decision problems. So basically, we assume there is a state of the network. This is the process in discrete time. It's a sequence x1 up to xn. We keep this general now. We assume this process takes values in some measurable Borel space. We assume there are k observation posts. This is the superscript that I denote here y1 up to yk. You can see my cursor, right? Is it?
Yep.
Yeah, okay, great. That way. So when I use this notation here, it means is just this includes all observations y1 up to time k. Superscript it index the observation post. Subscript is just the random process. So this 120 means the sequence from time 1 to time n. So again, these are the k observation posts, all data collected at this post, and then there are k control stations. And again, I use the same notation, superscript, distinguishing between the controls. A subscript is just the index of time. We assume this notation here are the actual spaces of the controls. So now let's see what it means delay sharing as it was introduced in the paper by Witsenhausen. And of course, many people work on this, especially Aditya and his collaborators, starting with his PhD thesis with Dimos Tenekegis. So basically, we say that there is a common information delta, which is known to all controls, but this information is known with some delay, capital T. So this is the delta. That means all controls, the K controls, know this quantity with some delay, capital T, can be 1, 2, and so forth. but each control has a private information component, which is only known to the K control at time t, which is this. I use the letter lambda at time t, K. So maybe you find this notation a little bit peculiar, because here I call the private information from t minus capital T plus 1 up to time t, and similarly for the controls. And the reason is because the rest of the information is already contained in the delta. So another way to look at this or to see this is think of the lambda t kappa as the private information component of the control kappa time t. That's the only thing that is private to each one of these controls. So another way to write it is the information structure of the K control is this I at time tk, which is the union of the delta, the common information component, and is private, because basically this is, if you put this together, is basically this kind of information and the private information of all others, but is received about with this kind of delay. Is it clear at this point? So basically, yeah.
About the notation, when you have the double subscripts, it means the time window between.
Yes.
Okay.
Yes. So basically, think of this. If no control was sharing anything, it means it would be only this information. Y from 1 up to time tk, u1 up to t minus 1 up to k. But because you receive delay information from all other controls with delay capital T, you have this extra thing here. Yeah? Clear?
Yeah, that's fine. Yep.
Yeah, I think this is the most important thing. So basically, the total information with delay sharing for the K controller time t is this delta and this lambda tk. In other words, this you can write it in this form. Okay? I want to distinguish, the reason I distinguish with this notation is because the only thing control K doesn't know is actually the private components of all other controls. It will become clear in a minute. I will write it down now. The strategies of the controls for each time t, control K knows this, which basically knows the delay shared, his private, okay? So with respect to all the information that is out there, the only thing it doesn't know is this lambda t minus k. In other words, the private information of all other controls, which is nothing more. All others means this quantity here. Is it okay? Clear, right? So control strategies, they use basically delta, which is the delay information component, and the private associated with the K. So centralized would mean the controls would know the same information. So that means I1 up to IK. Okay. That's the, I think once somebody understands this notation, which is kind of common, then everything else becomes kind of easy to follow. We assume we have a Markov decision, so the state follows the Markov property. The observations also, each one, there is a transition probability which can be depend on the controls at the previous times as well. The only thing I use a little bit different here is that the conditional distribution of the control at time t depends only on its own information structure. And I take this to be the Dirac measure concentrated at these deterministic strategies. It is not necessary. I could have worked directly with this, but because everybody's doing deterministic strategies, I do the same thing too, but the rest of the derivations do not make any distinction whether they are Dirac measures or randomized. Yeah. So basically there are two transitions S, Q for each observation, and then these are the strategies of the control based on their own information. Now we look at for the K tuple, and associated with this K tuple of strategies, there is a total cost, is a team cost, and the notion of optimality is this notion of decentralized team equilibrium, which means fix all the other players except the to their optimal values and minimize the kth one, and do this for all k's. This is the person-by-person optimality. And this notion is exactly the notion of Nash equilibrium. The only difference here is there is only one payoff. And strategies have different information structure. So as far as the K decision maker is concerned, all the other ones are fixed and optimized with respect to K strategy. Now, and of course, we already said that this strategy is what they depend on. Okay, that's the definition. It's not a new definition. It was known from the 1960s, 70s. Okay. Now, what is the objective that I wanted to pursue when I started this? I wanted to actually develop a dynamic programming based on this concept of decentralized team equilibrium or person by person, but I wanted to have something that retains two of the fundamental properties of dynamic programming, of centralized dynamic programming. The cost to go to be independent of the optimizing strategies. Optimization should be over the actual space, not over the strategy spaces. And then the second part is whether one can identify information states, meaning to satisfy some Markov property or extended Markov property, so that you can turn the problem into a tractable problem. And then, of course, if you can achieve this too, then you have the necessary sufficient conditions of the classical dynamic programming extended to decentralized based on this definition. So it means you have multiple dynamic programming equations. Like I said, the concept of definition, or person by person, if you wish, or decentralized team equilibrium is by Marshall and Radner, who developed this thing. What I think my approach is basically motivated by some work I have done on stochastic maximum principle using this notion of person-by-person optimality. So anyway, let me say a couple of things. One of the most fundamental results of static team theory is Radner's theorem of stationary conditions, who says that under certain conditions, which include convexity of the payoff, then any strategy which satisfies the person-by-person stationary conditions is also team optimal. Now, we have to be very careful because this is under static assumptions, and static means there is a random variable, there are k observations, the observations are function, they measure a random variable is some noise. Strategies are functions of the individual observations, and the goal is to find the team optimal. But because it is impossible to solve the team optimal, you end up solving person by person, stationary conditions. But then under convexity, you show that this is also globally optimal. That's one slide presentation of this fundamental result. Unfortunately, complete analog of this Radner's theorem, to the best of my knowledge and my experience, if you make the outputs to be a function of the strategies, or the state is affected by the strategies, the measure will be affected by strategies, and all this is off. But there are some variations you can do. Okay? Let me say a few things about previous work to put what I would talk about in context. Basically, long ago, in this should be IEEE proceedings, not IEEE, Witsenhausen had a proposition that such strategies that they use common and disprivate information, maybe they would be sufficient to consider this sufficient statistic, this probability distribution. This is the delay sharing part for all the strategies, and that this satisfies some recursion, and maybe this kind of strategies would be sufficient to include this, I would say, common information state because it satisfies a recursion, and this private. And then based on this assertion, several people worked by considering not the person-by-person approach, but to work with a single dynamic programming equation using as a cost to go to condition the payoff based on the common information, the delta. And this means one has to solve the team problem instead of person by person. And there were some important papers early on for one step delay. And of course, Aditya, Nair, Tenekejis, they wrote many papers, mostly on this formulation, to the best of my knowledge, when it comes to this delay sharing problem. I study all this, and I realize that one can get a little bit more out of this if he follows okay, let me skip this because basically, well, let me say a couple of things here. I kind of study all this past literature, and I realize there is another approach that one could follow a person by person. I found that's more natural if one wishes to generalize classical dynamic programming to these problems. with the objective to retain the properties of classical dynamic programming that I listed before. This is very important. Anyway, as far as these problems are concerned, there are, with respect to this area, basically, there were papers developing dynamic programming for T-step delay sharing. There was a paper by Witsenhausen on static reduction. Many people have referred to this. I work on this, generalizing it using Gustano's change of measure. It has some limitations. Let me not go through it. I work also on stochastic maximum principle, which using person-by-person optimality. Here, it appeared to me it is the natural generalization of Radner's theorem, but the conditions become a little bit different. You deal with Hamiltonians and so forth. You have necessary and sufficient conditions. I will skip it. And all these conditions vary depending on whether your sufficient conditions are with respect to person-by-person optimality, global optimality, and they are fundamentally different from necessary conditions. And all these have to do with minimizing the conditional Hamiltonian. And the measure that you use to do the minimization plays a fundamental role. I skip this. There is also recently I worked on the martingale approach. I skip this too. Let me go now to the standard. I give you the main idea. Okay, let's just recall first the classical Markov decision. We need a Markov process, a stage cost, and we know that under those conditions, in general, optimizing the cost centrally overall non-Markov property strategies, the optimal are Markov. And then because of this, of course, you can have a dynamic programming equation. Now, you notice the dynamic programming equation, the measure that you take conditional expectations does not depend on the strategies. And of course, the minimization is done over actions, no strategies. And this is the two things that we would like to keep and retain for these decentralized problems. Basically, these two key properties. And hopefully to get something like this for person-by-person optimality. Now, the starting point, since this is the goal, is we fix all the other strategies and we look at the payoff of the K strategy. Surely, we know that each strategy is a function, I put them here, is a function of the common information component and is private. The good thing is the private, this lambda T1, all the way to lambda Tk, these are all limited length sequences. So the first controller knows only this, but it doesn't know all the other ones, lambda 2 up to lambda k. So as far as this equation is concerned, if one was to do dynamic programming, the idea is very simple, basically. You say, the only difference between the centralized problem and this problem is that strategy gamma kappa does not know X, but does not know all these other private information components. Since it doesn't know it, the natural thing is to recondition on the information the strategy K has available and to bring into this a posteriori conditional distribution. Is it clear to this point? So if you're doing one-step delay sharing, this means this will be y, all the y's of the other players at time t. That's what it means. So it means he has to estimate those from his own data. So the first thing is you say, this is almost like centralized. Now let's see whether this a posteriori distribution satisfies a Markov property. Because if it does, then we are almost there. We can write the dynamic program. Well, it turns out this satisfies a recursion, okay, based on its own data. This, I call it the extended unobservable state of strategy gamma k, because this lambda minus k together with x is the state as far as the k strategy is concerned. Now, it turns out this satisfies a recursion. It depends on the actions in the right-hand side of this operator of the K control, and of course, the strategies of all other players except the K. That's why you need here this quantity here, because they have to be integrated out into this operator. So basically, this operator is just almost like the classical operator, but for the K strategy, it involves only the new sample of the output at time t plus 1 for the K strategy. Of course, it depends on all the strategies of the other players, but this is a function of this. That's why you need to you needed to extend the state. And then, of course, I put this to be the delta measure, so this is the recursion. And this is the recursion of this guy. But now you realize automatically that this operator is not Markov with respect to this evolution of this a posteriori distribution, because it depends on delta. But it turns out that it is Markov conditional on delta. That means conditional on the common information. This a posteriori conditional distribution is actually Markov, but you have to condition on delta. The other thing that comes from the recursion is that it does not depend on the strategy of the gamma kappa, and this comes from by induction. Okay? Now it's clear, right? Yeah, and of course, here is some assumption that one needs, otherwise you will not be able to derive that recursion. This is the assumption that is usually considering every time you derive that recursion due to the random nicotime derivative for it to exist due to this. Okay. So anyway, the first thing I thought, okay, let's look at the value function of the K strategy condition on all the other ones, meaning from T to the finite time N. Given all these things are fixed, we have to consider this condition of the information of the K strategy. That means this. And then it turns out that this is now you can get the dynamic programming. This, by the way, this is the first step that we do in partially observed. If before we go and use information states and nonlinear filtering, recursions, and so forth. Anyway, this automatically satisfies a recursion. You can see it is the terminal one, and it involves the a posteriori distribution, and then you also have the cost to go. I would show the recursion. This is the theorem. So basically, this conditional expectation, the dynamic programming at the final time satisfies this terminal condition, which is basically is using this a posteriori distribution. Notice that you integrate out whatever information is non-known is in the terminal cause that counts for all other players. Because the only thing that the K strategy doesn't know is the private information of all other players. That's consistent with this. This means this is a function of the information of the K player. And this is the integration part. This is the dynamic programming. This is the future cost. Now, if you go and plug in this guy here, it satisfies the nested, it has a nested property. It's a little bit of an ugly thing because it involves all these quantities. This guy is fixed, the U is fixed. This is standard even in the classical dynamic programming. The only things that I knew are this. This is meaning that it is only the private component of all other players at the time t minus capital T plus 1. That's all you need to integrate out. And then with respect to this distribution, but this distribution, you can express it using this a posteriori distribution. And at the end, this guy is just, it depends only on the a posteriori distribution, the private, and the control. So this is the new thing, the very first new thing that came out. And of course, the other thing that comes out is that this value function is independent of the strategy of the K player, and the minimization is over actions and no strategies, which is what we aim to achieve at the beginning. Two properties: information state or a posteriori distributions not to be function of strategies, and dynamic programming not to be a function of the minimizing strategy, but rather the minimization is over actions. Now, of course, it is natural now to go and say, okay, here you have you can see from the dynamic programming equation that if the infimum exists and all these measurable selection theorems hold, then your strategy at time n, your optimal U at time n is a function of the private and the a posteriori distribution, which is the private a posteriori distribution of that player. And the rest of the times, it will be these two again, but also the private information component of the K control. And then you can prove a verification theorem. Okay, everybody knows in this audience, these two, they are the classical versions, but generalized to this. Anyway, the assumptions, if you want to analyze also the existence of measurable selections, as far as I can tell, for finite spaces, you don't have an issue for issues related to measurable selections and existence of the infimum. Now, for abstract Borel spaces, the standard result of compact action spaces, lower semi-continuous bounded from below, conditions like you usually have on the per stage cost, and this weak continuity assumption with respect to this measure, they have to hold. And as far as this, if you have these conditions, existence of the ephemerum and also which occurs in the set, and also the measurable selections exist. That does not imply that you have fixed point theorems. That's another issue for these equations. Anyway, but now there is a second way to look at the previous dynamic programming equation. You can really, based on the previous dynamic programming equation, it's very easy to see that it depends on this private a posteriori distribution, the common information component, which is shared by all other players, and the individual private component of the K strategy. These equations here are simply, I rewrote the previous equations using the transition operator, here it is, of the Xi, because this is the future cost. So I simply rewrote it using that. It is nothing really new here. Okay, I use the recursion. Now here is the last part, and I think I would complete what I wanted to share with you, is this. This is very computational intensive because this delta grows with time, it expands. So we need another information state, or I would say a Markov recursion that contains this data. But it appears to me this is more straightforward now. I will explain why I said that. Anyway, the third dynamic programming is to identify a common posterior probability measure for all strategies. So basically, what I'm saying is, so far we have private a posteriori, but it's not Markov. It depends on this delta. This is the shared component, and it depends on this private information component. Now we need to find another probability distribution, conditional, that it will convey the information about this shared component. And the reason we want to do this because if this running T, it increases, there is no way to compute based on this dynamic programming. That's why we need to remove this delta. So basically we want a common information state for the data delta of this form. So the question is what kind of conditional distribution should we take? Whatever we take, if the objective is to generalize classical properties, then it should be a Markov process, and it should be independent of all the strategies. That's the two. If I keep these two as my objective, the answer is basically this. I don't know if there is another one, but surely this would do it. And one can see why this would do it, because this is global information up to that time. This is the state up to that time, and we know this is a centralized dynamic, a recursion of a posteriori distribution. This thing satisfies this recursion. It depends if you are given this data, it depends on the most recent sample, the control action, and the previous state, meaning this guy here one step below. But now he has this initial condition. Again, by induction, this does not depend on the strategies. This operator is the classical centralized operator, a posteriori distribution. And now this satisfies, okay, I put it down, but it doesn't matter. Everybody knows decentralized. Okay. And now we have a third dynamic programming equations by restricting strategies to separate, meaning what? We have a private a posteriori distribution based on all the data of the strategy K. We have the common to all based on the common data available to all strategies. That's the delay sharing part. And this is the private information component of the K strategy. Now, if you put this together, you can define cost to go with respect to this 1, 2, 3 states. And this satisfies the dynamic programming. And the dynamic programming is basically using the transition of this state, this, and this. And the conditioning is on the private information state a posteriori, the centralized private information component, and all this come because once you know the first three, you know this as well. Now, you have to do this conditional expectation, but you have all the ingredients to do it and specify this conditional probability distribution by substituting two transitions, one for xi, the other one for theta, and the actual private component. You will need this distribution, but this distribution is nothing more than the same we needed even for the first dynamic programming equation. The only difference is instead of having strategies to depend on delta, they depend on theta, which is a centralized a posteriori distribution. And this is basically the whole part. Basically what it says, the third dynamic programming equation based on this data for each user, which again, I wrote here in case the notation is peculiar. This is the common, all Y's, all U's. T minus capital T is the delay. For capital T1, this would be one step delay. Capital T2, two-step delay. And this is actually the private information component of strategy gamma kappa, of the K strategy. Basically, we found a way to compress this data using separate strategies. And this is private a posteriori distribution satisfies a recursion, conditionally Markov, a common or shared a posteriori distribution. It's a centralized conditional distribution. And the private information component of the K strategy. So it uses three. I tried to see whether you can remove this. I didn't succeed to remove this because I was thinking this distribution is already conditioned on, it includes this information, and I was thinking maybe it can be redundant. In other words, that since strategies depend on this conditional distribution that depends on this data through this conditional distribution, whether it's redundant, but I couldn't. Okay, so this is the best that I can see in terms of compression. And this is a question that Witsenhausen mentioned and was looking for in his initial paper, and he made some assertions that we should find some way to compress this data into information states that satisfy Markov properties. It turns out you need to use more than one. Of course, one can go further and derive another set of dynamic programming equations using a different common information state. But one choice is this, but if you use this, you will lose the property that this recursion is independent of strategies, okay? It appears the one that is independent of strategies is this. And it's very interesting because this one was actually mentioned by Witsenhausen in his paper to use this and only this in his strategies. But it turns out that you also need this. This is more fundamental in a way. You cannot get rid of this, okay? Anyway, the last thing I want to say is this. Unfortunately, I do not have any algorithm to solve these equations and results on convergence, okay? This, to my understanding, appears to be quite challenging. Okay, I will not say anything about this, but I wanted to see whether I did one thing. I said, suppose I take a completely separable example that I know. For this example, I know the answer should be the solution of two centralized partially observable problems solved separately, and then I add them up and simulate the first dynamic programming that appears to be very complex, and whether it produces the same solution, because if it doesn't, I have an issue. So I took two strategies, a vector with two components, completely separable. In other words, is the product of two. The outputs, again, the product of two. And the cost to be completely separable. Now, from the dynamic programming equation I presented, you can prove that this is the sum, the person-by-person optimal cost is the sum of two centralized problems. That was expected because of the separation, is fully separable. Now, a numerical solution of this produces the same results as the numerical solution of the first dynamic programming equation, so they appear to be consistent. And that's what we did some simulations based on some simple examples. Okay, I'm not going to present that result because basically we don't have any convergence proofs. So this is about it. I conclude this is a new dynamic programming approach based on person-by-person optimality. It retains the fundamental properties of centralized dynamic programming. Okay, you need three formation states, and it appears this is consistent with some of the other work that I've been doing. I noticed some similarities. I think what is important is to develop algorithms for this based on these dynamic programming equations. And with this, I think I'll conclude.